Good afternoon. Today I'm going to talk about proximal probe microscopy and lithography. So we're going to talk about three different types of scanning proximal probe tools. The first is scanning proximal probe interaction via electrical field. So we can use electrical field to modify the substrate under the probe. Then we can also use mechanical method, such as direct scraping of the surface and also exchange of material between the tip probes and the surface, and even moving atoms directly with the probe. Finally, we are going to touch a little bit on the advanced technique of near-field scanning optical microscopy. As you know, the diffraction limit forbids resolving features that are smaller the wavelengths of the incidence radiation that you use. For example, for conventional optical microscopy, we're talking about 200 nanometers. When you use even most advanced argon light sources, we're talking about, at the best, 50 nanometers. But the proximal probe techniques that we are going to discuss today allows us to go to atomic resolution and actually resolve individual atoms. So scanning tunneling microscope, the first real breakthrough in proximal probe tools, was invented in 1981 by Gert Bining and Heinrich Roer at IBM Zurich, the discovery for which they received Nobel Prize in Physics in 1986. So what is scanning probe tunneling microscope? It uses the small, less than 1 micron probe that is scanned over the sample with the very small gap between 3 and 10 angstroms. So the key to this technique is the very finely tuned control in X, Y, and Z direction, and it is used piezoelectric stage. So piezoelectric material is the material, ceramic, that changes the dimensions as you apply electricity. So close proximity between tip and the surface allows tunneling. Tunneling is the quantum effect. So if, for example, in real life, you shoot a projectile, such as a cannonball, into the wall, then you would know that it will either hit the wall or break the wall and get to the other side. While in quantum mechanics, it's a little bit different. You always have a non-zero probability that if you will shoot cannonball into the wall, it will get to the other side without destroying the wall. It was just on this side, and then it's on the other side. Now, that probability is very, very low, practically zero. Not zero, but practically zero. But then, if you would decrease the size of the cannonball, make the wall thinner and thinner and thinner, that probability goes up higher and higher and higher. So when you have a very small separation distance between the tip of the probe and the surface, the electron cloud from the surface and from the tip of the probe start to overlap. So basically you have charge jumping in between that space. So when you have a small space, you have charge going between the tip of the electrode and the surface, even though they are not contacting. So tunneling current is very, very sensitive to the changes in the distance between the probe and the surface. So if the distance changes by just 1 angstrom, the tunneling current increases by a factor of 10. So that sensitivity actually allows us to control the distance between the probe and the surface very finely. So there are 2 ways of controlling the probe. One is called constant current, another is called constant height. So we will use tunneling effect to control our probe. And we will watch a video right now where tunneling effect is described. So basically it's a video, nice video made by French company. They're explaining what quantum effect is of tunneling. So you can see as wall gets smaller and smaller, the electron waves will get to the other side. And okay, and now is the how tunneling microscope work. As you get probe closer and closer to the atoms, the wave electron clouds, they start to overlap, and you can actually sense each individual atom, right? So when we see the atoms, we don't actually see the atoms, we see the electron clouds. So in physical terminology, we see electronic density of states, okay? So this is how it works. You have your piezoelectric stage where you control tip, in X and Y direction, and also in Z direction. It's very important. So when you have tip, this is the red atoms at the tip of the scanning probe, and the blue atoms your substrate. Okay, so there is an electric current, very small, amperes, going between the tip and the probe. Okay, so there are 2 modes that microscope can work in. It's basically constant current or constant height. So when you have constant current, okay, it basically, in order you have a feedback, in order to keep current constant, your probe and the surface, right? There is 1 angstrom to affect your current 10 times. So it's very sensitive. So the feedback loop allows your probe to go up and down, with the same spacing as your surface. So it's basically like a glorified profilometer. It allows you to trace your surface. So when you keep current constant, you trace your surface. Okay? That's the constant current mode. When the constant height mode, basically, your probe goes along the surface, and then you keep change in current, right? As the distance increases, what happens to the current?
There's a constant drop.
Drops, right? It decreases. Your gap gets wider, right? And it's tunneling to lesser extent. Okay? And well, what is the dangerous part if you're using constant height? Well,
You run into the wall.
Exactly. You can hit it, right? So you have some sharp projection, right, from the surface, and then you are going to hit it. Well, if you have a constant current, then you can avoid it because of the feedback. It basically will go up as the surface goes up. So we use very small biases, and so when we look at the process data, as again you either process in your current, or you can process as what is more often just the height, the profile. Basically, it reflects what happened to your probe tip, goes up and down. So the key to all this technique is to have very, very sharp tip of your probe. Okay? So basically down to a single atom. It's very difficult to sharpen something down to a single atom, but there are some techniques. The one technique is electrochemical etching. Okay? So ability, to etch materials help us with the selection of probe tip. So for example, tungsten, well, you can etch tungsten to a very, very fine point. So here you have the picture of the probe tip. And the practical resolution of scanning tunneling microscope allows you to resolve about 2 angstroms. Basically, you can see atoms. And later in the lecture, you will see examples of that. This is really nice. It changed somebody's perception. You can actually see atoms. It's not just a concept anymore. And resolution is more than 1,000 times better than any optical systems. So here, as you can see on screen, is 2 examples. On the left, you can see graphite. And on the right, you can see silicon 111, including, as you can see, some defects in the structure. So that was principle of operation of STM. Do you have any questions yet about the STM, how it operates? There was a major extension of scanning probe microscopes a few years after that, after discovery of STM. And atomic force microscope was invented in '86 by Gerd Bienen, which was the same guy who invented STM. And Gerber, his colleague at IBM, and Professor Quat at MIT, and not MIT, at Stanford. Okay? The story is that Gerd Bienen took sabbatical or break, I'm not sure, from IBM and traveled to Stanford. So he was like a visiting scientist there for a year. They agreed not to make any invention during that time because it's a funny thing. At university, we can actually have very strict rules about IP. Whatever invented on campus belongs to university. So they made this explicit rule, okay, these guys, not to invent anything, not to invent any devices, maybe work on physics and so on. So long story short, I don't know what happened, but exactly after, Bienen left Stanford and came back, this invention was made, okay, AFM. And precursor to that invention is, well, let me outline the main problem, right, with STM. As we discussed, the way to measure the surfaces with STM is via tunneling current, right? So what does it tell you about the surface? What kind of surface should you have, your sample?
Conductive surface?
It should be only conductive surface, right? You cannot have an insulator because, you need to have conductor and conductor in order for current to pass. So, well, I mean, you can have metals and semiconductors with STM. This is very neat, but what about live cells? What about insulating? There is a lot of stuff that does not conduct current. So here AFM comes in. It also has other advantages, which I will cover in a second. But back to invention. So basically, it happened in '86. And the first commercial AFM was already in place by '89. Right now, AFM by far outnumbered its precursor STM for several reasons. The first one, well, you can measure both conductive and non-conductive surface, okay? Number two, it's actually very robust. It does not require vacuum. Okay? STM requires vacuum because remember the tunneling current, you need to have very clean, nice gap with nothing in between. Okay? AFM, I will describe you in a second, it's just kind of a profilometer. It just goes up and down along the surface. So you don't really need to have a tunneling current. You don't need to have an electric feedback. You don't need vacuum. So it basically measures force between very sharp tip, typically silicon or silicon nitride, and the surface. Well, if it measures forces, what kind of forces? What kind of forces do we have between surface and the tip? I don't have it on this slide. Great. So what kind of surface do you know? What kind of surface forces do you know?
Absorption?
Well, it's not a force, right? But do you know, let's say, capillary forces, okay? Let's say, you know, van der Waals, there are many different forces. Typically what happens, okay? You have very sharp tip, you have surface. So you actually have monolayer of fluid, typically, condensed on your surfaces. So what tip measures, and people are very actually kind of confused what forces are there. They first thought it's like van der Waals forces. It's, you know, van der Waals is kind of polarization forces. It's, you know, if you have two molecules, they are polarized on each other, and you have this kind of basically electrical force, which van der Waals force. But for AFM, the main force would be capillary force between the surface of the tip, between the tip and the surface. And it basically goes and drags a pool of liquid around. So atomic force microscope, again, you will have our friends piezoelectric stage positioning. One thing that you will have, so you will have force feedback on the cantilever. And the positioning of the cantilever would be given by a laser. So laser shines down to tip of the cantilever, it's kind of back side of the cantilever, back through the mirror, and you will have, you know, an array of light-sensitive diodes that will give you the position of the tip. Okay, so you measure force and you know the position, and you can analyze your data in the computer. So AFM works very much like a profilometer. You don't really need to have conductive surface or any specific rules of what kind of surface it should be. But again, you need very sharp, very nice tip. And typically, those tips are etched in silicon and silicon nitride. As you know, if you will have wet etch of silicon, it will have, you know, for people who took my, you know, biomems class or other classes, they know it's basically, you have a very nice edge along the, you know, preferential directions to have this very sharp pyramid. So if you can see silicon tip, for example, you know, will have a very sharp point. So AFM techniques have three different modes, okay? The contact, non-contact, and it's called tap-in mode. So in contact mode, we have tip that basically touches the surface and kind of slides along the surface, right? As it slides along the surface, you know, we know the position of the surface. That's basically like a profilometer, and it provides the highest resolution. But the problem is, you know, you incur damage to the surface and you also wear off your tips. So the second mode is non-contact mode. So non-contact mode, basically, you have a vibration of the tip, okay? So you have your tip going up and down in the resonant frequency, okay? As it goes closer to the surface, okay, your resonant frequencies start to change. So the closer tip to the surface, the lower resonant frequency. It's because now your surface starts to affect your tip. So as you lower the resonant frequency, well, you can observe that, right? Because you have this laser shining on the tip. So you know what the frequency is. So you can deduce features of the surface. Actually, this is what's called vibration mode AFM. And we have Professor Kumar Vikramasinghe on our campus who participated in inventing that mode of AFM microscopy at IBM. So the last mode, which is most commonly used, okay, is called tapping mode. So you do touch surface, okay, but not all the time. So as you go along the surface, you touch it periodically. So you can, kind of scan your surface by points, okay, whenever you touch the surface. So it's basically similar to non-contact because it's like vibrating in between. So it's kind of probe in non-contact mode, but then it combines it with nice resolution at the moment it touches the surface. Okay? And this is tapping mode, so it basically taps the surface. This tapping mode is what is used most widely.
So how often it switches between two modes?
So how often it touches the surface? Well, it's up to the user. It's basically you tell. If you want highest resolution, you touch it all the time. So if you decide to touch it, every couple of nanometers, that's fine, or 1 micron. So you're still collecting information about the surface, but it's just non-contact mode. So it's up to you. It's also, but the more often you touch the surface, the more damage you incur to the surface as well. So here is the typical picture of AFM. It's 100 silicon surface, and it is scanned in non-contact mode. So you can see here the profiles, okay, in 2 different directions. So you really, you can resolve individual atoms. And here are, another examples of AFM. You probably, if you have ever seen AFM, it's more typically it's like that. It basically gives you the complete, 3-dimensional profile of the surface, which means X, Y, and Z direction. So those mountain ranges. So here it actually tells you the scan of the gold structure sputtered on the glass substrate at room temperature and after annealing at 300 degrees C. So comparison of 2 techniques, scanning tunneling, microscopy, and AFM. So we know that STM works with conductive samples. AFM can work on both conductive and non-conductive insulating. STM measures tunneling current, and AFM measures forces. And I said mostly it measures these surface forces such as capillary forces. So STM is non-contact. AFM often makes a direct contact with the surfaces. It can also work in non-contact mode, but highest resolution is when it actually touches the surface. This is the big one. STM works in vacuum, okay, which basically limits somewhat its usefulness. Well, AFM can operate in liquid and gas environment. They both have comparable resolution. People, if resolution is your goal, people actually prefer STM still. And for another reason why STM is so cool, but we will touch on it later in this lecture. And as a result, AFM has been adopted on much wider basis. So now more universities and corporations, they have AFM than STM, even though AFM was invented, as we discussed, later. So AFM was just the first in the whole series of scan and probe techniques. Okay? So more tools have been invented. So the first STM, then AFM, now electrochemical microscope, where you actually study electrochemical properties of the surface, thermal properties of the surface. You can use capacitance, right, between the probe tip and the surface. It's actually capacitance microscope, magnetic force microscope, and pH probes. Okay? And the key for the rest of today's lecture is that those proximal probe tools, they can be used for surface modifications. So they're actually tools for micro and nano fabrication. So the first one, we will talk about electrical field-induced chemical modification. The simplest one is oxidation. Okay? So as you know, you have, the oxygen atmosphere. You have, let's say, silicon. You apply bias, and you produce chemically, electrochemically derived silicon oxide. So that basically, I just described what you would do. So you have silicon, you have probe in the vicinity, use it as an electrode, and locally you can form a silicon oxide, which you later can use as a mask. Okay, so you already studied classical lithography in this class. Is it correct? Okay, great. So this is basically like that, but your oxide now is determined by where you applied potential with your probe. So you apply small bias, 2 to 20 volts, and electrochemical oxidation takes place on the proximal probe. So it's very locally. It can be applied to semiconductors or metals, and then you can use it as a pattern in several ways. So if you look at this picture on the left, right? Again, it's IBM Nano. So you can see that first we used it to produce an oxide. So you can see IBM Nano is actually raised letters, okay? So they're above the surface. You form an oxide above the surface. And then the next step was actually to remove oxide. So why, when we remove oxide, this IBM Nano still left? Can anybody tell me? Let's think how oxide is produced. What did we do to produce oxide? Where did we take this silicon for silicon dioxide? We took it from the surface, right? We took it from the surface and we produced oxide. So when we etch out the oxide, what's left behind are the grooves, okay? Where silicon used to be, and we converted to silicon dioxide. We removed the silicon dioxide, and now you have letters, okay? So as you can see, the whole, you have see bar there. So the whole structure, the width of that bar is 100 nanometers. So we have, about 30 nanometers, maybe thickness of each letters. Now the depths, we can control depths to fraction of nanometer. Can control depths very, very well. Because, oxidation is very well, process that we controlled very well. Do you have a question?
Yeah, so if you did this on a surface that did not form an oxide, I'm saying that it doesn't make a component of silicon dioxide. If you did something that just is completely, like let's say you just put the oxide on top of it and it's not connected to the surface at all.
Right.
And you etch it, it would just wash everything away and it would be completely flat.
So can you repeat your question? So,
So I was thinking when I saw that, I didn't think that it was this, in my opinion, it's obviously wrong, but in my opinion, it wasn't the silicon dioxide formation that made that etch, when made that, that imprint IBM Nano.
right,
I thought it was that when you etch with HF, it etches everything at an equal rate, so, oh, okay, no. Sorry, I was thinking out loud right now.
Okay, no problem. But it was the oxide. It actually etched out the oxide. But when you look in the profile, when you form an oxide, right, film, and people in semiconductor industry use it all the time. Actually, what happens is not that you have a flat surface and on the top of it you have an oxide. Actually, when you look at the profile, the oxide goes down as well as up. Right? Okay, so speaking about the surface that cannot produce oxide, or alternative ways of actually having a lithography. So we can use very thin resist that is assembled from self-assembled monolayer, SOM. So we have an alkanthiol, ultra-thin monolayer on the surface of gold. And basically, as tip goes close to the surface, it pretty much shaves, okay, the monolayer, and you produce a window. And how do you know if you can actually have a window where you took your monolayer off? In order to confirm that you have a window, you conduct an electrochemical analysis, because at that places, right, you will have a redox reaction, and at other places you can actually have a no current, right? You will have an isolated surface, and then you open that surface. So here you can see the STM tool to be used to produce 60 nanometers by 60 nanometers window in the picture on the left. Okay, so we will return to use of self-assembled monolayers as a resist in a little bit in today's lecture. Okay, so we can use this in a multi-resist system. Why do we need to use multi-resist? Well, remember that for STM, what kind of surface do we need? Conductive or insulating?
Conductive.
We need to have a conductive surface, okay? So what we use, if you look at the cross-section of different layers, so we have a silicon substrate going from bottom up. Then on silicon substrate you have an oxide. Then on oxide you have amorphous silicon. So that's the key. We need to have an amorphous silicon, because amorphous silicon is your conductive layer. You will be applying current between this amorphous silicon and the probe tip. So then you have silicon dioxide, and then you have self-assembled monolayer. So basically what will happen, you apply your current between the between the amorphous silicon and the probe, and you shave off, open the window in your self-assembled monolayer. But self-assembled monolayers, they're so thin, okay? They're only 2.5 nanometers thin. They cannot really be very effective mask to be used for etching silicon itself, because it takes a long time to etch silicon. So what we do, we open that window, okay, and then we use that top mask only to etch our thin layer of anodic silicon dioxide. And then anodic silicon dioxide is already more robust layer to etch layers below. So it's kind of, we're doing it in stages. First, okay, we used self-assembled monolayer, and we use that as a mask to etch layers beneath. That layers beneath, you use it as a mask finally to etch your silicon. Okay, so you use your multi-layer resist to do your etching in steps. And this multi-layer resist technique can produce, as you can see, this picture of the etched silicon is 50 nanometer thick or 50 nanometer thin grooves, okay, done in silicon. And this is AFM picture of this pattern. So you can use actually your scanning probe lithography more efficient than your e-beam lithography. So let me ask you one question. Have you covered e-beam lithography in your previous lectures? No? Well, I will remind you. So have you covered regular lithography?
Yes.
Yes? Okay. Remember that in your lithography, we have in I think second slide, we talked about this Rayleigh or Abbe's, formula, diffraction limit. Your resolution improves if you have shorter wavelengths, okay? So actually, if you use your electrons and ions, it is more efficient, better resolution than just visible light, okay? So invisible light is just hundreds of nanometers, and you go into nanometer and range when you decrease wavelengths of your source. So you improve your resolution, okay, when you go to e-beam, electron beam lithography. You can produce finer features. But e-beam has one disadvantage. It has backscattering. So it can resolve the features, okay? But when electrons hit your wafer, let's say you have a wafer, and on that wafer you have a resist. So it goes through the resist, through the window. It hits, it goes through the resist, it hits backside of your wafer. But then it's so energetic that it will backscatter and basically broaden your profile, okay? So it starts developing, wider channels. So when you have a proximal probe, which just hovers above the surface, like in scanning tunneling microscope, you can actually pass current from that tip to the surface and use that tip as your, as your exposure source, right? As the source of electrons. And because it so hovers just above the surface, you can actually use that, in your lithography. The electrons produced from that tip needs to have much lower energy than conventional e-beam lithography. And basically, this is what it said. Your e-beam lithography needs much higher energy than your scanning probe. And your scanning probe basically can produce finer features. You can have more control in your lithography. And the key to your resolution is to have very, very sharp tip, as we said. So you can even use a nano tube attached to a tip, and now that will be your tip. So, if you go to, do you use textbook in this course? No? So one picture I have seen in Professor Madhu, 3 volumes. In the second volume that discusses topic of proximal probes, he has a very nice picture of the proximal probe tip, and then the nanotubes actually attached to the probe. Okay, so you can use nanotube at the tip of your probe to improve your resolution. So we can have less than 10 nanometers lateral resolution. So it's very important. At this point, we discuss that our resolution is, it would depend on the sharpness of the tip, right? Our resolution also depends on, the fidelity of the stage that we have, right? The piezoelectric stage. It's also very important what kind of resist you use. So people are working with all kind of different resists. So this is CMC4R resist that allows you to have very, very fine sub-10 nanometers. I think they achieve 8 or 7 nanometers resolution. If you remember from previous slides so far, I talked about 60 nanometers, right? And then we go into 50 nanometers, 30 nanometers. Here we will have 7, 8.
What are you showing on the photo?
Yeah, so what we have here is basically the molecular resist you have. So resist consists of organic molecules, okay? So each molecule is only, several nanometers in size. So they have the molecules internally, they strongly bonded to each other, but they have only weak intramolecular bonding. So the hydrogen forces van der Waals. So when you apply bias between the tip of the microscope and substrate, you basically take those molecules away. You open the window, okay? And so this is characteristics now of your resist, that you can open very, very small windows in that resist. So here, for example, you see line C on the top of your picture. It's actually 7 nanometers lateral resolution. So what is important here is lateral. In height, we can have less than 1 nanometer resolution, very, very nice. But in lateral, in XY, this is where the battle is. So 7 nanometers is the best resolution achieved. Right now it's the paper of 2011, but this is about, current resolution where proximal probe lithography allows us. Well, finally, you can just use tip of your microscope as a scratching tool. Okay, you can just scratch the surface. So here is you have Don Quixote and Sancho Panza from Picasso's, okay, sketch, and this is scratched out on piece of polycarbonate plastic. Okay, just use tip of AFM, I think, and they just scratched it out. Okay, so you can also scratch a resist, for example, just open the window. Okay, it's one of not very sophisticated technique, just directly write it. And if you use self-assembled monolayers, right? You can have a very nice resolution, but even directly you can have like 20 nanometers. So incredibly fine resolutions are possible. And then you can use a heated tip to improve your resolution. So here you have picture, AFM scan when 21 nanometer lateral resolutions have been achieved. Okay, fun part. We can actually manipulate individual atoms. Okay. So in November of '89, and that picture actually prompted me to go into material science. Okay, so when I was a student, because I came to the United States in 1990, and I saw that, and I said that, well, this is incredible. How can they do that? I still did not know for a long time how did they do that. So I will tell you today how they do it. So they did it with STM, okay? And I will tell you exactly how. So they spelled the world's smallest IBM logo So this thing was done in the, at IBM on nickel with xenon atoms, okay? The reason why you can't do that, because for STM, not AFM, STM, you actually have current, right, going between the probe tip and the surface. So you can use that current to affect the atoms, individual atoms on the surface. So you can do two things. First, what's they call in lingo parallel movement. Basically what it means, you can, scoop, just probe the atom to go from one place to another on the surface, okay? So basically what it goes, it means that adhesion between the tip of the microscope and the atom, right, this electron cloud overlap, for a second is stronger than between the atom and the surrounding atoms on the surface, okay? So it almost looks like you're taking it a little bit off the surface and, you have lateral force and it lands, okay, next to its location. And then you do it again and then and again. So you can kind of use directed diffusion, if you will, because in fact the atom kind of never totally leaves the surface. And then you can also have atom kind of stick to the tip of the probe, and you can take it completely off the surface and put it on another surface. So for example, if you can take atom off the xenon surface, okay, substitute your nickel surface and put it down, and then use it to position individual atoms. So it took Don Eigler, the guy who actually did it, and his team, 1 week to put together this IBM logo, okay? So let me see. This is a short video, if we're lucky.
20 years ago, IBM fellow Don Eigler's discoveries changed the course of nanotechnology.
Can you hear
On
it?
September 28, 1989, Don Eigler became the first person in history to move and control an individual atom. Shortly thereafter, with the help of a custom-built microscope, he and his team spelled out the letters IBM using individual atoms, signaling a quantum leap forward in the field of nanotechnology. Dr. Eigler built his scanning tunneling microscope in order to visualize and experiment with individual atoms and molecules. As he experimented, he discovered that it was possible to slide individual atoms and move them using the tip of his microscope. To demonstrate this ability, he created the world's tiniest IBM logo, made from 35 xenon atoms. Dr. Eigler's accomplishment remains, to this day, one of the most important breakthroughs in nanotechnology. At the time, the implications of this achievement were so far-reaching, they almost seemed like science fiction. But now, 20 years later, it's clear that this was a defining moment that has spawned the kind of research that will eventually bring us beyond anything ever imagined.
When we wrote IBM with xenon atoms, we did it with actually quite a few motivations. The primary one was scientific. It was to demonstrate that we really had control of atoms at the atomic scale and that we could position atoms in a way that's very similar to how a child would build something with Lego blocks. You take the individual blocks, put them where you want them to go. And then we had to demonstrate that we could do this over and over again with atomic level precision. So putting the atoms into a regular pattern was one way to do that. That worked out very well.
Understanding the properties, movement, and interaction of various materials at the
That's pretty
nanoscale
cool. They use a
is
joystick
essential for
to
one
actually
day
slide
building
the
smaller,
atoms.
faster, and more energy-efficient processors and memory devices. This understanding could eventually enable a whole new level of personalized healthcare and targeted treatments and therapies. Already, the ability to understand and manipulate atoms is leading to new kinds of fabrics, products, and more. Because of Dr. Eigler's seminal work, scientists continue making breakthroughs that continue driving the field of nanotechnology. The exploration of building structures and devices out of ultra-tiny components as small as a few atoms or molecules. Such devices might be used as future computer chips, storage devices, biosensors, and things nobody has even imagined.
Okay, so the idea here that we can position individual atoms. What can we do with individual atoms? Any ideas? What, if we can position individual atoms, what is possible? So what, let's say now you can move individual atoms. What is possible now if you will move individual atoms? Make new materials, yes, material synthesis. That's what we will come to that point in a second. What else?
Some of the protein is like by shape, right? So you can manipulate the shape, and that's what they mentioned about the medicines, targeted medicine.
Right. You can also encapsulate also the drugs, for example, with the special like protective surfaces. What you can do, the big one, is you can actually store a lot of information now on the surface. Because imagine that if you have one atom, right, it would be like 1. If you don't have atom, it would be like 0, right? Ones and zeros. You can store a huge amount of information, up to like theoretically possible maximum now on the unit of surface. Well, of course, there is also a drawback, okay? So we'll talk about drawback of this whole wonderful technology in a second. But that inspiration of, moving atoms, you can see all kind of demonstrations. So that was, on the left, original demonstration of 4 atoms, xenon atoms, I think, platinum. So it's 4 platinum atoms separately and 7 platinum atoms all together, right? So you can do it with STM tip, actually, herd them all together, separate them. And then in a high university, they put their logos, okay, and the smiley face on the right. So it's actually, pretty nice, right? So you can do individual atoms. The major drawback, okay? The major drawback is, are we there yet? Is the speed, okay? How fast can you do that? Okay? So it took researchers 1 week to position 35 atoms of xenon on nickel substrate. So how long will it take to create 10 micron long, 1 micron wide, half a micron high line? Any ideas?
Age of the universe.
So what is age of the universe? Do you remember?
13 billion, something, 13.2 billion, right?
And well, I'm not sure. Maybe I think 4, but maybe you're right. Maybe it's
4 is age
that 4 is age of
the Earth. Probably.
Earth. Okay. Okay. So it takes 5,000 billion years. 5,000 billion years, okay, to put together that line. So it's actually forever, okay? So you need very dedicated researchers to do that, okay? So what is the solution, okay? So if you would like to assemble, well, of course, putting together xenon atoms and, manipulate in 1 week, it's an overkill. You can do it now faster, right? But in any case, the only solution for mechanosynthesis on more realistic scale would be massively parallel processes, okay? So you would need multiple heads, okay? As you do, one thing, it's not one, you need thousands, okay? So you need massively parallel processes to create something from bottom up. So this is storage millipede data storage device that has 4,000 AFM tips. I don't think it went anywhere, but it produces a big buzz that, at one point, IBM was doing all kind of, promotions to advertise that they're going to do this storage module, like the storage media. And actually, Gert Binnick, Nobel laureate, who participated in creation of scanning tunneling microscope, and then AFM was involved in that effort. So it could not compete with the solid state memory, right? But at least they demonstrated that we can have parallel processes, okay? So we can have this, it's 4,000 tips. And in a second, I will demonstrate to you even larger, number of proximal tips working together in deep pan lithography. So what is deep pan lithography? So you can, deep pan lithography takes its name from, writing implement, dip pan. So you dip it in the ink, right, and you write it down, and then you dip it again, and you write again. So people who were doing AFM, they have been forever irritated that fluid, would collect on the AFM tip and go down to the surface, right? It wet the surface. So that fluid that goes back and forth between AFM tip and the surface is actually a nuisance to them. And then researcher Chad Mirkin, who was doing this research at Northwestern, said, interesting, maybe we can use it, okay? So he used polymer ink resist, right, on tip on AFM tip, and used it to draw lines, okay, on the surface. So you can actually use this to produce lines on the surface, and you can you can use it. So in this case, this thing is will assembled into a layer of resist. So and the lines itself, they can be as thin as the latest one, 15 nanometers. So these techniques of deep pan lithography can, well, for example, on this picture on the left, you can see 30 nanometers wide line of ODT. ODT is the organic ink that is primarily used for deep pan lithography. There are many inks and substrates combination, but very often it's ODT on gold. Resolution depends on many different things. As you know, on paper, if you have very grainy paper, right, your resolution actually decreases. So you need to have a fine substrate. The contact time, the longer your tip is in contact with the surface, you also have spreading of the ink. Your writing speed affects it, therefore, you also have a big effect of humidity, okay? But it's feasible to integrate microfluidic technology in order to have the tip of your AFM, to have ink go to the tip of your AFM. Because right now you need to ink the tip of AFM all the time. The same thing as deep pan, right? So, but in the future, it's probably future development that it can be simplified, and we have long continuous lines. So up to 55,000 of these AFM writing tips were done in parallel. You can see the picture on the top, right, of these AFM tips to draw. So each of the picture on the background is actually a small, you can see this is the 100 micron scale. And so this is a couple of microns. You can actually see the picture of head of Thomas Jefferson from US Penny, right? And Thomas Jefferson, the features on the head is 80 nanometers. Okay? It's pretty impressive, huh? So 55,000 copies at the same time. It took only 30 minutes to draw it. So I think this is very promising.
How long did it take to make the array?
30 minutes, 3-0.
No, but the tool, to make the tool.
Oh, to make the tool itself. You know, it doesn't take the 55,000 cuts together. I don't think it takes, I don't think that, first, it didn't take them years, so it's okay. But number two, you can use the same array, you know, for a long time, right? And each tip is just a silicon, right? So you can very easily etch it. And the key is here, you can use it at the same time, right? You can do them all at the same time because it's photolithographic process. So you use it, you use the mask, right? You take the mask off, you etch it. So you can virtually have all of them done in like one day because basically it could be just a one wafer. You can use deep pan lithography not just to have normal lithographic process with organic resist. You can also use it to pattern biological molecules, such as proteins, for example. So what you have here is one of Chad Mirkin's studies where he used deep pan lithography to do immunoassay. Do you know what immunoassay is? So immunoassay is basically a test to see if you have certain proteins in your body or not. Okay? So you have molecule called antibody, okay, that reacts to a certain protein. So when you have that protein, which is called antigen, and antibody, they kind of stick together, okay? So you can immobilize that pretty much very much like a pregnancy test, okay? So you can see if, for example, you have a certain proteins, if you're sick with some disease. So it's a diagnostic tool. So what, in this study, AFM tip and deep pan lithography was used to pattern, create a microarrays of two different types of antibodies, so two different types of proteins. So it was lysozyme and immunoglobulin gamma. Okay, so you can distinguish. You know, if you have, for example, flash your antigen to which part of microarray, okay, it will attach. So basically, what kind of conditions you have, right? What kind of proteins you have in your body. So that, you know, you can see why is the reason. Right now we have already all these immunoassays. Why do we need to use this tool? The idea is because if you can do it at nanoscale, okay, you can use let's say drop of blood, okay, very little of the sample to conduct wide variety of tests at the same time. So, you know, nanotechnology will affect healthcare as well. So you can use even more effectively deep pan lithography, deep pan nanolithography, it's DPN abbreviation, if you don't have liquid ink, but you have solid ink. When you have liquid ink, it evaporates, for example, okay? So when you have solid ink, what you do, you heat up the tip, okay? And then you deposit your ink only when you heat the tip. So you can also improve your resolution that way. You can avoid evaporation. Okay, so here you have a picture when it said, you see when you have 25 degrees C, you don't have any ink in. 57 degrees C, no ink in at all. About 98, you have a little bit, right? And when you have 122, the melting point is 100. When you have 122 degrees, then you have a lot. So you can actually pattern, your lines when you want it, when you heat up the tip. So using thermal DPN, you can also use it in the same environment where you use your conventional semiconductor processing. They have a lot of exposure to vacuum environment. So with this technique, you also can have it in vacuum as well, if you want. Okay? Very quickly, two other types of microscopy, or basically it's a one type of microscopy I would like to touch on very briefly. It's called near-field scanning optical microscope. Okay? The same way when you have tip very close to the surface. So today we talked about the scanning, the tunneling effect, the interaction of the charge, okay, between the surface and the tip. You can, if you can have the light issuing from the tip on that distances much smaller than the wavelengths of light, then it doesn't matter. The diffraction limit will not apply. Okay? So in near-field scanning optical microscope, you can actually use optical techniques, because optical techniques are attractive, right? They're not destructive. You basically just use light, right, to study surface. You're not poking anything around. They're inexpensive. So the idea of using this light, okay, was this very, what's called near-field regime, was first suggested in Singer. He wrote in 1928 to Einstein, suggesting him the idea, and Einstein thought, oh, it's a neat idea, but it will never be realized, because he didn't know about, nanofabrication. So actually, it was realized. So the first demonstrated in 1972 in microwave regime, and then in optical regime in 1984 by Poole and co-workers. So what you have is the tip that contains the waveguide. So it's very sharp. The waveguide itself is basically need to be on the order of nanometers, maybe 30 nanometers. So you have pooled glass with the very sharp tip, and you have light, okay, coming from the tip, going through your specimen sample and collected here by objective. And what you can see is the high resolution near field scanning optical microscopy. You can resolve features of 30 nanometers. So it's a 30 nanometer film, and the holes itself is the 100 nanometers. But the problem is you need to pass light through the very, very thin fiber. And that is disadvantage because you have a very low illumination, right? The light need to go through the fiber. So several people, among them actually, Professor Vikramasinghe suggested what is called aperture-less near-field scanning optical microscopy technique, where instead of having the waveguide, you will have just a shining tip, and you will shine the light onto the tip, and from tip it will be scattered onto the surface. So you can have also, very nice resolution in the nanometer range. So this is I'm telling you about now, this is what is happening right now. People are trying to improve this technique now. It's still, we're still not using it as a lithographic tool yet, just a microscopy, but it's probably just around the corner. So do you have questions up to now? Yes? No?
What then, for the previous slide, does it need to have a transparent sample now, or with this?
Yes, you need to, because the light need to go through. So, if you don't have questions, then I think I will stop at this point. Thank you very much.